Here in this question, you can see that we are asked to design a common gate amplifier that has the gain of 5. One thing I noticed from marking your quiz number 2 and number 3 was that a lot of you have problems actually reading the question. So like for example, for quiz 2, we had mu n Cox is equal to 4 times mu p Cox equal to 100 microamp per volt squared. And a lot of you couldn't actually even plug in the numbers. Like you couldn't actually use the fact that, well, mu and Cox is 100 understand the fact that mu and Cox is 100 microamp per volt squared, and mu p Cox is, well, 4 times less than that, so 25 microamp per volt squared. These are very basic stuff, but I guess the stress of a quiz or the exam might actually affect your performance. So the most important thing in the beginning of solving a question, and especially a design or analysis question in the electronic circuits, is that to actually understand the question and read the given data carefully. So the gain is equal to 5. That's output to input, V out over V in. Rs is equal to 0. So basically it's telling us that this resistor is actually 0. And R3 is 500 ohm. So let's just write it down here. 1 over Gm is 50. So if 1 over Gm is 50, therefore Gm is equal to 1 over 50, therefore, which is equal to, well, 20 milli. And the unit for Gm is amp per volt, so it's going to be 20 milliamp per volt. So I just made this 1,000 milliamp, so it became 1,000 divided by 50. That's how I got 20. Power budget is 2 milliwatts, and VDD is 1.8 volts. From there, I can actually get my current. We're going to get to there. And some other parameters are given. So mu and Cox is given, the threshold voltage is given, and the lambda is 0, so there's no channel length modulation. So what is not given? We have to find out what is RD, R1 and R2. The current flowing through the transistor, the DC current, ID. And of course, for the transistor, we know that mu and Cox, but we don't know W over L, the geometry of the transistor. So those are the things that are not given. And well, similar to all other circuits that we deal with, these capacitors are assumed to be very large. So we know that if we're talking about DC analysis, they're open, and when we're talking about AC analysis, they are short. Okay, so the first thing we want to think about is that it's kind of like reverse engineering. We have the solution, we know the gain is 5, we have to find out what was the circuit that resulted in this gain, right? While we satisfy all the requirements from the question, which is basically the main one is the power consumption, right? So if I want to design a circuit here that does not burn more than 2 milliwatts, but gives me a gain of 5, and with this resistor R3, what kind of RD I should put here, and what kind of a transistor size I should put here, and then perhaps once I have the ID, I can somehow find this gate voltage, and then from the gate voltage I can easily find R1 and R2, because we know that it's a simple, because this current is 0, it's a simple resistive divider here, right? So R1 and R2 are, well, I know that I'm not too concerned about them. I'm going to find them out in the end. The most important problem right now that I have is basically the most important questions to be asked is what is RD, what is W, and what is L, okay? To get started, I would say, well, gain is 5, but then what is the gain expression, right? For this circuit, if you look at the last slides of the previous video, you would see that for this circuit, we got the gain to be V out over V in to be equal to R3 in parallel with 1 over Gm over R3 in parallel with 1 over Gm plus RS times GMRD. So the whole point was that we knew the gain of a simple common gate amplifier is simply GMRD. And then because we have some sort of a voltage attenuation at the input between RS, R3, and the resistance looking from here to the source of the transistor, which is 1 over GM, then we got this resistive divider attenuation factor. That's how we got the gain. But now that the question is telling us the RS is 0, so if this is 0, then the denominator and numerator are the same thing in this fraction. They cancel out. So my gain is simply GMRD. Okay, so if I want this to be 5 and GM is actually given to me, I can easily find RD, right? From these calculations, I can say that RD is equal to basically 5 divided by 20 milliamp per volt. So I'm going to get 5 divided by 20 times 10 to the negative 3. So that's 5,000 divided by 20, 500 divided by 2, so 250 ohms. Okay, great. Now I have my RD. How about ID? Well, I have to make sure that, so the budget is given to me, so I know that basically my power, and when I'm talking about power, I'm always talking about DC power. At least in this course, like when we want to talk about AC power, we say AC power. The power consumption is really the DC power, because the AC power is very negligible. Why? Because we have, from the beginning of this course, we have talked about the fact that all of the signals in the electronic circuits that we discuss are small signals. So the fluctuations are very small. The peak to peak of that signal is very, very small, in the order of millivolts. So most likely the power consumption is going to be extremely small. So we're going to really talk about the DC power consumption all the time, because that's the average power that is being drawn from the VDD. So my VDD has two currents. So let's call this ID, and let's call this I bias, right? There's nowhere else that I have a current being pulled from a DC voltage, because my input is an AC source. So when I'm doing DC analysis, my input is as good as a ground, and anywhere else I just don't have any battery or any power supply, right? So I have only IB and ID. So my power is going to be equal to VDD times IB plus ID. Therefore, I can say that the power consumption of 2 milliwatt, 2 times 10 to the negative 3, is equal to 1.8 times IB plus ID. If I do the math, I get IB plus ID to be 1.11 milliamp. Now, the first question that I have to ask is, well, how much of it is ID and how much of it is IB? Because I don't have any other equation, it's like a one equation, two unknown, and I have to make a decision, and I have to be very smart about it. I have to be a good engineer, a good designer about this. So I have to think about which one of them is actually more important. Thinking about IB, I would say, well, IB is a current that is basically used for my biasing circuit. It flows through R1 and R2 so that I can get the voltage that I like to have at the gate voltage. So by setting the R1 and R2 ratio. So is it important to get like basically can I get this voltage as long as the R1 and R2 ratio is the ratio that I want? Does it really matter to have an IB that is 1 milliamp or 1 microamp or 1 nanoamp? So like if you think about it, generally it doesn't really matter, because I know that this VG is equal to R2 over R1 plus R2 times VDD, no matter what is the IB, because the IB is going to be flowing through here as well, because there's no current going to the gate of the transistor. So whatever current that I'm actually spending here is going to be wasted. So it better be actually a small current, because if I have 1 milliamp there and it's just being wasted, well, it's not a good use of my power consumption. I better have, like, I'm going to reduce that 1 milliamp. Why do I even consume that much power, right? However, for ID, I know that ID and GM are related, not linearly, but they're related. The more ID I'm going to get out of a transistor, I'm going to get the more GM out of it, because I know that GM is 2ID, for example, divided by VGS minus VT, V threshold, right? So I know that for the same overdrive voltage, for the same VGS minus VTH, the higher ID results in higher GM. Well, we have some other equations that shows that like they have a square root kind of a relationship, but they always go up together, maybe with different rates depending on what we keep constant. But then it's always better to have an ID, better to have a higher ID if you want to get a higher GM so that we can get a higher gain. So in this case, it means that, well, I want to actually put as much as possible of my current to ID rather than IB, right? Because of all of these discussions, I make one of my design decisions and say that I'm going to go with ID equal to 1.1 milliamp and IB equal to 0.01 milliamp. So I gave 0.01 milliamp to like 10 microamp to bias current just to have some decent amount of current flowing there, and the rest of it to my drain source current. Okay, so that's the first decision that we made. Now, if you make the decision that ID is 1.1 milliamp, the first thing we have to make sure is that this is a current that doesn't make my transistor to go into triode region, right? How do I check that? Well, first I have to find VDS, and then I have to find VGS minus VTH, and then compare them, right? So let's look at that. So R3 is given. First, I want to calculate what is this source voltage, and then calculate what is the drain voltage so that I can have VDS, right? So V source is R3 times ID, and it's going to be 500 times 1.1, so 550 ohms. V drain is going to be VDD minus RD ID. So it's going to be 1.8 minus, we got the RD to be 250 times 1.1. Okay. So it's going to be equal to 1.525. So from this, we can say that my VDS is almost 1 volt. So to be exact, 975 millivolts. Okay. So now I got my VDS. I have to first calculate my VGS to make sure that my transistor is working in the saturation region. How do I do that? Well, I know that from here, up here I wrote GM is equal to 2ID over VGS minus VTH. I have GM, that's 220 milliamp per volt. I have ID, I have V threshold, I can find VGS, right? So GM is equal to 2ID divided by VGS minus V threshold. And if I do the math, and I encourage you guys to actually do the math, because a lot of you lost mark because of just your being a little bit careless during the plugging in numbers and actually calculating the values. Okay, so GM is going to be, if I do the math, I'm going to get, well, I do have the GM. VGS is going to be equal to 0.61 volts. Let me rewrite this. Okay. Now, knowing that VGS is this and V threshold is 0.5, I know that I'm deep in saturation, so I shouldn't have any concerns because my VDS is almost 1 volt, VGS minus VTH is 110 millivolts, so it's like far larger than the overdrive voltage, so I'm fine and I'm in saturation. The next thing is, now I have RD, I said that I need to find out what is the W over L. Well, knowing that I'm in saturation, I can say ID is equal to 1 over 2 mu n Cox W over L VGS minus V threshold squared. Therefore, I can say that my 1.1 times 10 to the negative 3 is equal to 1.2 times mu and Cox is 100 microamp per volt squared, so 10 to the negative 4 amp per volt squared times W over L. And then VGS minus VTH squared is going to be 0.11 to the power of 2. That is going to be 0.0121. Okay, so from here I can actually calculate W over L. Okay, now the last thing I want to do, so it's just basically doing the math. It's a one equation, one unknown. I trust that you guys can actually do this. The last thing that we want to calculate is the R1 and R2. Now, knowing that the VGS is 0.61 volts, VGS is 0.61 volts, and I know that V source I calculated up here is equal to I calculated as 550, sorry, that should be 550 millivolts. So 500 ohms times 1.5 milliamp, I'm going to get the 550 millivolts. So Vs is 0.55 volts. Therefore, I can say that Vg is equal to 1.16 volts. Now, I know that Vg is equal to R2, so Vg is equal to R2 over R1 plus R2 times VDD. So I can say that 1.16 is equal to R2 over R1 plus R2 times 1.8. And on the other side, I know that the current through R1 and R2, so VDD divided by R1 plus R2 is supposed to be 10 microamp, so 10 to the negative 4 amps, or actually 10 to the negative 5. Therefore, 1.8 divided by R1 plus R2 should be 10 to negative 5. So I have two equations, two unknowns. I get R1 and R2. Okay, so that's how I actually find R1, R2, RD, and the geometry of my amplifier. The procedure is actually the opposite of what we do when we analyze a circuit. When we analyze a circuit, we generally have the resistor values, the transistor sizing, and everything that we need, and we are expected to calculate the gain, the input resistance, output resistance, and so on and so forth. For the design questions, it's exactly the opposite, right? But then the information, like the knowledge that we actually use to solve these questions is exactly similar to what we use for analysis questions. Like the key equations that I used to actually solve this question was, first of all, I used the fact that the gain expression is this. So if I don't know, like first I need to know what is the gain expression. That's the exact same thing that I need to do for analysis, right? So like if I want to calculate the gain, first I need to find the expression and then I plug in the numbers. So first I needed to know what is the gain expression, and then the other equations that I've used are basic equations. I've used the basic DC current equation of a MOSFET. I've used the relationship between, like up here in the left, let me use the orange so that it's more visible. So I've used the relationship between GM and ID. I've used the resistive divider kind of a relationship. It's all about like very basic questions. You just need to know what equation, basic equations, and you need to know what equation to use at any time, right? And what order you should go. So when the power is given to you, you need to find the current from the power. And then once you have the current, you need to see, okay, so like how do I relate this current? Because I know the moment I know the current of a transistor, I can kind of calculate the R naught of a transistor and GM of a transistor and so many other things. If those are given to me, then what is not given? Like for example, in this case, W over L was not given. So knowing ID and knowing GM, I could calculate W over L, right? So again, I would encourage you to actually solve the questions in the assignment 9 and 10 to get more and more kind of practice problems on these topics, because that's the only way you can actually learn these topics.